It's a great pleasure to have Olga Mula with us today here. Olga got her PhD in applied mathematics at Sorbonne University, and then she was a postdoctoral fellow at RWTH Aachen University, and then a researcher at INRIA Paris. And she is currently an tenured assistant professor at Paris Dauphine University in Paris again. So today, I'm really looking forward to this talk. It's going to be kind of interdisciplinary at the intersection between machine learning and optimal control. So I would like to encourage the speaker, Olga, and thank you again for being here.
Thanks a lot for the kind invitation and the kind introduction, and it's a real pleasure to be here. So today we are going to speak about recent work I have done with my former postdoc, Joubin Aguili, who is now at the University of Strasbourg, on depth adaptive neural networks from the optimal control point of view. So the main topic is neural networks, and the main motivation why I jumped into this field is obviously the same as everybody's, I guess. We are seeing outstanding achievements with neural networks in a number of various applications. And just to give an example, here is a state-of-the-art result in which this is a classification problem with 1,000 classes and more than 1 million images. And thanks to neural networks trained with more than 60 million parameters, we are capable of classifying 1,000 different elements like this mite in this complicated object, in this complicated picture, or the classifier is capable of telling you that there is a motor scooter in this kind of picture in which even the human eye would need a few instants to realize that there's a motor there. So these are really very impressive results, especially from numerical computations and experiments. But so even the proponents agree that there's a lack of theoretical understanding. And so I just wanted to try to contribute a bit to this. And the way we are going to do this is by exploiting a connection that exists between neural networks and the theory of optimal control problems and ODEs. The first part of the talk is going to be devoted to explain this connection for those of you who are not aware of it. And for those who know, I hope that you nevertheless learn something out of it. The second part of the talk is devoted to this contribution we made with Joubin Aguili on depth adaptive neural networks. And the main goal was to try to understand what was the role of depth in these neural networks. What can we really achieve by going very deep? And how we can find a systematic way to choose a good architecture for a given problem, because maybe we don't need to go so deep depending on the application. Also, one of the questions that we wanted to study was how we could help in the search for good quality optimizers in deep architectures. The difficulty being there that when we have a very deep architecture, we expect it has a high approximation power, but the number of parameters involved is going to be very large. Therefore, the minimization problems are going to be in higher and higher dimension, and optimization techniques are a bit limited in this respect, and we are going to converge probably to local minima. So the contribution I'm going to present should be seen like some thoughts on how we could understand depth and how we could try to go in the training in order to benefit from this depth. And all this is going to be explained through the connection with optimal control. So let me go to the first part of the talk then on this optimal control theory. And for this, I just first would like to introduce a bit the definition of a neural network and the the setting in which we are going to work, which is supervised learning. So as you probably all know, neural network requires to define a so-called activation function, which is going to be defined here as a function sigma that acts on scalars. Usually this function is nonlinear. For example, the ReLU function is taking the max between 0 and the input x. We could think of other types of activation functions, and in particular for our experiments we use the hyperbolic tangent, for example. Once we have fixed this activation function, we need to define some network architecture, and we fix a number of layers, capital L. And for each layer, we are going to define a width, which is going to be given by this index P1 to P capital L. So having prescribed this, a neural network is a function that goes from P1 being the width of the first layer, and it goes to RPL, PL being the width of the last layer. And the characteristic of this function is that it is a cascade of compositions in which the main building block is an affine application, WI, followed by the application of the activation function to every entry. The affine map, WL, so it has to have input and output dimensions that are in coherence with the width that we have prescribed. And since it is an affine map, we can represent it via the application of a matrix A to our input vector plus a certain offset vector B. And these matrices are going to change, of course, at each layer. Having said this, neural networks have been proven very successful when they are used for supervised learning tasks. So let me remind quickly what we are going to understand by this. The setting is supervised learning is that we have a certain function, psi dagger, which somehow represents the truth between process that we want to understand. It takes as input it takes values in a certain input space X, and it sends us to a certain output space Y. This psi dagger is going to be unknown to us, and it represents some sort of truth in the process which we actually would like to represent and approximate accurately. Typical examples are, for example, in regression, where the input space is going to be Rn, the output space is going to be the Euclidean space Rk. Another example could be classification, where the input is in Rn and the output is an index between 1 and k. The goal in supervised learning is to approximate this truth function psi dagger with a certain function which is going to be parametrized. And the setting goes as follows. So we don't know psi dagger, but we have observations of its effect. We are given a set of data, observed data, which are pairs xi, yi, where the yi is assumed to be the output of the application of our psi dagger. Again, psi dagger is unknown, but we know its effect on xi. And we know this for a number n of samples. We are going to try to give represent an approximation of this psi dagger by using a parametric family of functions. The parameters are going to live in a certain parameter space, which I encode in the notation here via this upper class theta, and it this may be a very large dimensional space of p parameters, for example. And what is going to happen is that we are going to consider a certain approximation class of functions where the input is our input space X, but in addition, we consider theta as an input here, and we map into the output space Y. And the goal is to discover a good value, a lower class theta star from our parameter space, such that when we fix the value of this parameter, theta star, in our approximation class, and we view this function as a mapping from X to Y, then this must approximate as accurately as possible the truth function psi dagger. In the setting of learning with neural networks, the approximation class is going to be a family of neural networks with a certain prescribed architecture. We are going to prescribe the activation function, the number of layers, and also the weights that we have in each layer. And this is going to generate a family of functions, which is going to be our neural network class. The parameters in this case, which I wrote here as theta, they are going to be the coefficients of the matrices A, L, and BL that are included in our affine applications at every layer. Having said this, we need to somehow explain how we are going to select the parameters AL, BL in this setting. And in general, in the supervised learning methodology, we go a bit like with a probabilistic approach, and we are going to assume that there is a probability mu on our input space X. We are also going to introduce a certain loss function on our output space, which is going to encode a certain notion of distance. And in the ideal setting in supervised learning, what we are attempting to do is to look at the distance between our true function, giving the true output psi dagger of X, and our output psi of X. We look at the distance and we take the average error over all possible inputs following the distribution mu. Having prescribed this objective function, which depends on the parameter, the task in supervised learning is to find a minimizer of this loss function. And this would give us, in a sense, the best approximation of our psi dagger with our family of neural network functions. The problem is that, in general, since psi dagger isn't known, and since also the distribution mu is also unknown, we cannot really solve this this ideal setting in this form. And instead, what we have is a fully data-driven setting in which we have observations xi, which we suppose that are taken iid over mu, and we observe the outputs yi. And what we are going to do is to suppose that mu follows a uniform distribution, although this is wrong. But we suppose this, and then we consider the empirical loss of our observations. And we look for the best parameter theta star on this empirical loss. So now, obviously, there is this theta star, this minimizer, is going to depend on n encoding the number of samples and also the samples that we have been given. And so one important question is the one of knowing to what extent, when I solve this data-driven problem here, am I very far from the ideal setting, which is the one I would like, in fact, to place myself, but I cannot. So there's a lot going on in order to try to explain the success of this supervised learning with neural networks. And so far, I don't think that there is like a complete and cohesive theory that explains everything. And there are studies on many types of directions. The first is on the expressive power of neural networks, and this works done, for example, by the community from approximation theory, which they are very active at the moment in improving this kind of results. Another type of result that is being pursued at the moment are statistical risk bounds. And for example, there have been some interesting results on the VC dimension of neural networks. Another direction of research is the one of optimization in high dimension, because solving this empirical loss involves minimizations in high dimensions, because the parameters are going to be very numerous. And therefore, so there's a lot of research on stochastic gradient descent, on the energy landscape of these loss functions. And finally, there's also another angle of attack in which there is an interpretation of neural networks and the supervised learning as a dynamical system. And this is the approach that we have taken in our contribution. The questions we have tried to understand, or at least shed some light into, are how to discover automatically a good network architecture, and how to facilitate the training of neural networks. And the main idea that we wanted to see whether it was true was whether we could somehow do the training by increasing the depth of the neural network, and whether this was helping in finding better quality minima for this supervised learning task. In order to define, in a sense, what would be the limit of many of the depth, when we take an infinite depth, in a sense, we have placed ourselves in the setting of dynamical systems, because it allows us to define a continuous depth limit. But it would be very interesting if we could somehow go to the derive the same result, but without the theory of ODEs. Here's the connection of supervised learning and neural networks with ODEs and optimal control. So recall that a neural network is a function that was this cascade of compositions, and at each layer L, we can view the process as taken an input vector ZL, we apply the affine mapping WL, and then we apply the activation function. This gives us the next step, ZL plus 1. So suppose now that the input and the output dimensions are kept constant. In other words, P1 equals P2 equals to P capital L. The widths are the same. And what has been observed is that some neural network architectures can be seen as time schemes for ODEs. The prototypical example are ResNets, in which we take, to go from one layer to the next, we take the previous layer, we add this perturbation through the activation function and the linear or affine mapping, and this is going to give us the next layer. Obviously, we can somehow make a conceptual jump and think that this is the discretization of an ODE, because it looks a lot like a forward Euler discretization. There have been other connections with other types of discretizations. For example, polynets are approximations of backward-Euler discretizations, and fractal nets are connected to Runge-Kutta schemes. When the little perturbation h here tends to 0, then the neural network is going to become an ODE, and the function f is now going to be the solution u to a certain ODE at a certain final time capital T. And so what is going to be the ODE? So the ODE is going to be, so the derivative of u is going to be equal to the activation function applied to u and to some parameters theta t. So the parameters theta t are what I denoted here as the matrix. It's the linear application, the linear mappings. It is taking, the ODE is taking as an input function, as an initial condition, it is taking our observation x. So every time we observe a new xi, we have to assume that we propagate forward a solution of a PDE involving the activation function. And now the parameter theta t is actually going to depend on time continuously. So we have the graph of a function eventually, which ranges between time 0 and time capital T. So in this view, the supervised learning task is going to become an optimal control problem, where the loss function is going to be the distance between our output y and our observation output y and our solution to the ODE at the final time capital T, starting from our input observation x. We may, in addition, add some regularization terms, as is also usually done in the plain neural network learning approach. And like before, we are going to try to minimize the loss over the average of all the observations. And eventually we have to minimize the loss. Similarly as before, since we cannot solve this ideal setting because we don't have access to an infinite number of observations, what we are going to do is to replace this average by the empirical mean. And in addition to this, there's another detail, which is that we said that the output that we provide now is a solution to a certain ODE. And in general, this ODE, we are not going to be able to integrate it exactly. And therefore, we need to involve some solver. And it means that this solution is going to be slightly perturbed due to the action of a solver. And we are going to assume in the following that the solution which is provided by the solver integration is giving us a function which is at epsilon distance from the true one. So there are somehow two discretizations here, the one of the average and the one of the integration of the ODE. And the goal of our paper was to understand whether we converge and how we converge if the accuracy of the integration solver becomes tighter and tighter, and as the number n of observations tends to infinity. So our goal was to prove that when these two discretizations go to the perfect ideal setting, so whether we really converge to the ideal setting. And so in passing, actually, what we derived was an adaptive algorithm in order to come as close as we wish to this ideal setting. So the idea goes as follows. to describe it, I need to introduce, I need to recall how the minimizers of the sampled setting can be characterized by optimal control. They are characterized by the so-called Pontryagin maximum principle. It works as follows. So we introduce what is called a Hamiltonian function. And what we know is that we have a sufficient condition to characterize the optimal parameter theta star n here. And it says that if a theta star is an optimal control to the sampled problem, then there is going to exist an adjoint state, which I call here P, such that so we have the solution to the ODE, as I described before, and we are taking as an initial condition the input data xi, and the co-state process is solving another ODE which goes backwards in time, because so the initial state is at the final time t, and it is involving the solution u at the final time t and the observation yi. And having this co-state process p and the solution u, the optimal control theta star is characterized by the fact that it maximizes the Hamiltonian, in the sense that this function here, when I evaluate it in the last variable on the optimal control, then this is going to be always larger than any other choice of the parameter. So this somehow characterizes the minimizers of the optimal control problem. And it actually gives a hint on a numerical scheme which we can follow in order to find this minimizers theta star. It is a method called successive approximations, which has been known for a very long time already in the literature. So the method is a fixed point method, and k is going to be the index of our iterations. The method requires that at each iteration we have to solve. We start with an initial guess of our parameters theta, and we are going to solve first the forward dynamics, taking as initial condition the values xi of which have been observed. Once we have solved this, we are going to solve the backward dynamics of the adjoint state p. So we start from the final time t. We take the output of the forward dynamics, and we look at the distance with the observation yi. Once we have done the forward and the backward dynamics, we try to maximize the Hamiltonian condition. So we have to solve for every instant t. We have to find the maximum in theta to this problem here. And this is going to give us the next value of our parameters or optimal control in this iterative procedure. What we have known for already a long time is that this strategy converges to the optimal theta star, but only locally, meaning that we have to already start from a very good guess of the minimizer in order to converge to it. An extension of this, which I learned on a paper by Weinan E and his collaborators, is that if we fix some parameter rho and we define this augmented Hamiltonian, which involves our original Hamiltonian, and we add this extra penalizations here on the behavior of the forward and the backward dynamics, then it turns out that we can prove that the PMP has the same minima as the original Pontryagin maximum principle with the plane Hamiltonian. And this is important because, in fact, now the convergence to the minimizer is global with the extended Hamiltonian. So if we replace here in this strategy the Hamiltonian by the extended Hamiltonian, then we can start with any starting guess, and we are going to be guaranteed that we are going to converge to the minimizer. One observation at this point is that in the strategy I have just outlined, we have not really discretized time yet. So we have to do ODE integrations, but I assumed that they were solved exactly. And this is in practice not the case. And the usual approach is here at this point to assume that we discretize first and then we optimize. And the problem with this point of view is that we lose the connection with the infinite, with the non-discretized framework, our idealized setting, which is the one we would like to resemble. So since we lose the connection with the continuous formulation, our approach was to propose an adaptive discretization, where we progressively integrate more and more accurately the ODE in order not to lose sight of the continuous formulation. And the idea is to do exactly the same algorithm as I have introduced, but now the forward and the backward dynamics have to be solved at a certain target accuracy, epsilon k, which has to be carefully chosen. And we are going to tighten across the iterations in order to guarantee that we eventually converge to the fully continuous setting. Also, the maximization condition, which is maximizing over the Hamiltonian or the augmented Hamiltonian in order to guarantee global convergence. We can prove that, in fact, we don't need to reach the maximum here. We proved that, in fact, we can solve this problem at a certain, up to a certain accuracy, which I denote here by gamma k. So gamma k is a parameter that is ranging between 0 and 1. And it means the following. So if we consider the maximum of the Hamiltonian problem that we have to find, it suffices actually to find a control, theta k plus 1, which comes at a factor gamma k of the maximum. Imagine that gamma k is, for example, 0.8. It means that we just need to maximize the function up to a factor 0.8 close to the real maximum. And this is important because at this step, we have to involve a certain optimization method to compute this Hamiltonian. And there we try to go with the best optimizers we have. In practice, in our work, we used LBFGS algorithm. And this algorithm is iterative. And therefore, the starting guess is going to play an important role. And the fact that we are allowed not to find the exact maximum, but a certain relaxed maximum is, it seems relevant to me because in general, these optimizers, even the LBFGS algorithm, is not really going to be able to catch the exact maximum. So for this algorithm that I just introduced, where we tighten the accuracies, we could prove the following result. So assume that we have n samples, and assume that we tighten the accuracy across the iteration following certain rules, which I cannot detail more in the talk because it would become too technical. We also have to tighten the accuracy at which we do the Hamiltonian maximization across the iterations. And then what we can prove is that if the parameter rho from the augmented Hamiltonian, if this rho is taken sufficiently large, then the sequence of controls theta k that we are going to compute with our scheme. So this yields a minimizing sequence of the sampled supervised learning problem, in the sense that the loss function evaluated at our parameters theta k that we have built, it tends to the minimizer of the sampled problem as k tends to infinity. As in addition, the sequence of controls theta k's is monotonically decreasing, which is what this relationship is expressing. So we have proven now that our theta k's are a minimizing sequence of the sampled problem, and it remains to connect our algorithm to the fully continuous problem where we look at the average and not just the empirical loss with the observations. And there what we could prove is that the value of our loss function from the sampled problem and on our computed theta k, it converges to the minimizer of the fully continuous problem with high probability, and the convergence is exponential in the number of samples. We were able to prove this result using again some results that we found in another paper by Wine and collaborators. So this is it for the presentation of the algorithm, how it works and what we can say in theory. We did some numerical examples, and the goal was to try to disentangle the impact of several elements. So the first is what is the impact of the number of samples? Also, the refinement strategy in the integrations of our ODEs is important, and something that is unfortunate with our theoretical result is that it doesn't really give a hint on the exact refinement algorithm that we have to use to really achieve all the hypotheses of the theory. So we have to try different refinement strategies and see what they give. Also, the starting guess for the Hamiltonian maximization with the LBFGS algorithm is important, and so we also try to understand what was the effect of the initialization.
Excuse me, Olga. There was a question a while ago for maybe clarification. You might have already answered in some slides, but how is the discretization of the optimal control related to the discrete time optimization problem? That was a question that
so how is the I cannot see the chat.
How is the discretization of the optimal control related to the discrete time optimization problem?
How is the discretization of the optimal control
related to the discrete time optimization problem?
So that was my question. Maybe I follow up with a slightly more aggressive question. Why would I solve all these difficult discretized control problems when my machine learning colleagues are perfectly happy with just running SGD until things fall into place? I mean, I can see the theoretical benefit, but I don't see the practical benefit. And I mean, you have to solve so many things, and then you talk about LBFGS. I mean, they're going to have a nervous breakdown if they're going to use LBFGS. I mean, it's a beautiful method, but I've never heard anyone talk about LBFGS, unfortunately. So that might be playing devil's advocate a little bit.
Yeah, so thanks for the question, because I think many people from machine learning I mean, I have this kind of question. So first of all, our contribution is rather theoretical. So we did an attempt here to give the latest, best neural network procedure that is going to beat the state-of-the-art ones that are currently in the market. The reason why this is maybe conceptually appealing is that, well, I forgot to say, and this is very bad, that this, let me go here, this is the algorithm essentially. The backward dynamics is in fact the backpropagation in the classical neural network. And so as far as I know, sometimes there are some instabilities in the backpropagation. And with this point of view, in fact, you realize, but just realize this is not really going to give us a new state-of-the-art method. You realize that this is due to the fact that somehow there is an underlying discretization when you are doing this backpropagation. It's as if you were solving maybe too coarsely your backpropagation. And with this method, for example, one appealing feature is that the backpropagation is done more and more accurately across the iterations, and therefore the stability, for example, of this step is going to be guaranteed, I mean, asymptotically across the iterations. So this is probably maybe one of the most important practical things that one could keep in mind with from our contribution. And yeah, I mean, beyond this, I don't think that we have developed, as I said, anything state-of-the-art and which should replace state-of-the-art algorithms.
Okay, thanks.
Yeah. Does this answer the question or?
Yes.
Yeah, okay, thanks. So, well, let me just present a very simple example where the goal is to approximate the graph of the sinus function. So it couldn't be easier. We take an activation function as the hyperbolic tangent, and we do our algorithm with the adaptive steps. And so we tried several adaptive strategies here. So as a discretization technique, we used explicit Euler because this is resembling a lot like ResNet. And we started from 3 layers at the beginning of our iterations, meaning that we had 3 time steps. One layer here is going to be a time step. And we refined progressively until 32 layers or time steps. Unfortunately, we couldn't go beyond this 32 because there were some memory issues that were arising in our program, and we couldn't go beyond, but it was already enough to show what is the effect of going deep in the number of time steps, therefore in the number of layers. To see this, we consider 3 refinement strategies. The first is an abrupt refinement, where at iteration 250, we went from 3 time steps to the 32 time steps upfront. The second type of refinement was fast refinement, where we had 10 time steps every 50 iterations. And finally, we considered slow refinements from 10 time steps every 100 iterations. So we iterated over 800 iterations, and we considered n sample observations. This is the value of the loss function in the trainings that we got. We compared our approaches with exactly the same procedure, but we were not refining progressively the time steps, and we considered a shallow network for all time steps with only the 3 time steps, and we consider also a deep a deep ResNet with 32 time steps at every iteration. What we see here is that there are some adaptive strategies that really seem to be getting significant better minimizers for the training. And in addition to this, if we then consider the generalization errors, which are given in this picture, we see that there is, again, a slight gain on going adaptive. And this is to be compared to doing the training with the full 32 layers up front from the beginning. Somehow we get better quality minima, and it seems that the generalization error is also a bit less robust. And well, so I think we are running out of time, and this was more or less what I wanted to say. We have a couple of other tiny little examples, but I mean the main message was somehow conveyed in this picture. So just to conclude, the main...
Sorry, you have plenty of time if you want. I mean, just to clarify, because still 10 minutes. You could even talk for 10 more minutes. So
I thought it was like 45 minutes or so. And
no, sorry. I mean, no, you have plenty of time. Don't rush. Yeah, don't worry.
So I won't take you long. Just maybe conclude by saying that so we made this study on depth adaptivity in the framework of optimal control. As I said, this is not attempting to be state-of-the-art method from the implementation point of view, but it is attempting to explain how maybe we should do adaptively the training of deep neural networks. And our results reveal that this adaptivity helps to find better quality minima. And there is more robustness in generalization errors. So now, as further directions which we could consider, I think it would be interesting to consider the final time t adaptively also in the algorithm. And one issue of this type of approach is that the number n when the number n of observations becomes large, we are going to start finding memory issues. And there are some strategies which we could think of, like coarsening or other methods which are called shooting methods, in which we could address these memory issues. Finally, another idea is that, in fact, these ODE nets, perhaps one idea to make them really more convincing for the practitioners, it would be to mix them with classical neural networks and use the fully connected layers of a ResNet, for example, and treat them like a neural ODE, but the rest and treat them like a classical neural network. And finally, as I think I said at the very beginning of the talk, I guess it would be really great if we managed to derive the same kind of result in the same spirit, but without the framework of optimal control and ODEs, and directly in the framework of neural networks and supervised learning. And with this, I thank you for your attention.
Okay. Thank you. Thank you, Olga.
Thank you.
So, yeah, so I will open the floor for questions if anyone has any more questions. Let's see, you can either unmute yourself, Tim. Yeah, please go ahead.
I think this is more a general question, which I should probably know the answer to, but why is it that basically using more layers always, to me, sounds like just adding parameters to your model, but the generalization error seems to get better. But to me, that's kind of counterintuitive, that because if you add more and more layers, isn't that like overfitting at some point?
Well, yes, this is one of the risks, of course. But the benefit, on the other hand, is that you can gain more approximation power with more layers. And so there's this trade-off, which you need to, I mean, yeah, you have to try to gain more than what you lose. And so the little results that we had went in that direction, in the sense that although it was looking like overfitting here in the training, it was not, because the generalization was more robust.
Yeah, that's why I was confused there, but that would be win-win.
Yeah, so this is a win-win, but so it depends on the example. For example, we had another very simple toy problem in which this is what we observe for the training. So there's no significant difference in the level of the value of the loss function when we train. But again, when we look at the generalization, it seems that there is really something to gain with respect to that.
Okay, thanks.
Okay. Okay, I actually had a couple of questions. One question was about this parameter. I think it was called gamma k. Probably this like the thing that is quantifying how far you are from maximizing.
Yes.
The objective, right? So how can this be estimated? So is this somehow estimated, or is kind of
we don't know how to estimate it. So one of the main frustrations, so to speak, of this work was that, yeah, we pinned down a pretty nice theory. We could prove a lot of things, but in practice, we cannot really estimate this gamma k, for example. And also, the theory is giving you rules to tighten these epsilon k tolerances, but it involves certain quantities which are very difficult to estimate in practice. And therefore, when you go to an application, you need to refine, but it is not providing you a totally closed strategy and formula to address your problem. It is only telling you that you need to refine.
Yeah, I see. Okay. Okay, so another question I had. So there's kind of, by construction, this kind of interpretation as a dynamical system is constraining you to have layers of the same size, right? That's kind of,
yes.
Is it possible to break this somehow with, I don't know, some trick to get rid of this assumption?
So far, I don't know. This is it seems this is really necessary, and as I said in the conclusion, in fact, maybe one trick is to include this ODE net in a bigger net where the layers are changing. But apart from that, I don't have any clue so far on how to play with the depth. And there's also another very big constraint that I did not comment on, which is the fact that where can we see this? Excuse me, I need to navigate on the slides. In general, so even if you have a fully connected deep neural network, at the end there is in general a reduction operation, which, for example, takes you from a vector of dimension 5 to just a single scalar value. And this is like the terminal application of the neural network, which is here written as a function g. And in the classical neural networks, this function is optimized upon. But in ODE nets, this you need to fix this. There's so there are two constraints there, which I guess, make a lot of harm to the approximation power with these ODE nets.
Okay. Okay, so is there any other question from the audience? Let's see, that's, I don't see anything in the chat for now. By the way, do you also have any experiment with classification? Because now you were showing us the regression problem. So how this framework works with classification?
So we can also do classification. Unfortunately, I didn't add the little example that we have.
Okay.
And so it can work too. I'm sorry, I didn't add the example on the slides.
Okay, so it's okay. It works.
Yeah, it's we have a preprint on this, and there you can find it. And we are actually also considering now a slightly larger classification problem.
Okay. Oh, there is a question in the chat from Olivier. So can we have different sigmas in the definition of F, or it must be fixed?
Well, I guess we could perhaps imagine that until from 0 to t/2, we have some activation function, and then we change. And I mean, this would complicate a bit the theory, for example, but I think this is doable. We can, I think we should be able to account for this in this methodology, yes.
Okay. So let's see if there are no more questions. Any burning questions waiting? Don't be shy. Okay, so let's thank Olga again. And yeah.
Thanks a lot.
Yeah, well, yeah, thank you again for being here.